Hi, my name is Hira Shaheen, and today I am going to start set theory. So let us start with the basics of set theory. What is this set theory? You can say set theory is a branch of mathematics that has its root from ancient times. Okay, so if you have seen, it has root from ancient times and has evolved into a powerful tool for describing the structure of world around us. Okay, so we are discussing about the background of this. So at its core, set theory is the study of collection of objects known as sets and the relationship between those sets. From simple everyday objects to complex mathematical structures, sets and their properties can be used to model and analyze a wide range of phenomena. Okay, so set theory has played a critical role in development of modern mathematics. So set theory is a branch of mathematics that deals with the study of sets, which are collections of objects that share common properties. So remember this. What is this? Common characteristics, or you can say common properties. So it is a collection of objects which share some common properties. So now see, we will study in the later videos all these topics related to sets. So sets, relations and functions are the important concepts in mathematics. So see, set is a collection of distinct objects which can be anything such as numbers, letters or even other sets. Sets are usually denoted by braces. For example, the set of all even numbers can be denoted by this 2, 4, 6, 8. Okay, or if you can say that if we are saying the set of alphabets, suppose the set of alphabets is denoted by this name, is this set name. So what are the letters in this? A, B, C, D till capital Z, and it can be have the small letters also, small a, small b, small c, and till small z. So all this will be the set of alphabets. So generally we can take only the capital letters or only the small letters. But if it is not mentioned, we can take both of them, capital letters and small letters, all. Okay. So now see, we can, just now you have seen set of even numbers. If I say set of natural numbers, if the set name I denote it as capital N, so it will be 1, 2, 3, 4 and so on. Set of whole numbers, so we know that it starts from 0, so 0, 1, 2, 3, 4 and so on, comma. Okay, so see, next, sets can be classified into different types based on their properties. Here are some common types of sets: finite set and infinite set. So what is this finite set? Okay, finite set and infinite set. See, what is this? Finite and infinite. A finite set is a set which has a specific number of elements, while an infinite set has an infinite number of elements. Just now we have seen like set of even numbers. If I say set of even number, so it will be 2, 4, 6, 8 and so on. We do not know if it is a whole, so 0 will also be your even number, 0, 2, 4, 6, 8 and so on. So it can be till infinite. All the numbers which are divisible by 2 will be your even number. Okay. So that is infinite. That is infinite. So that is infinite set. Now see what is finite set. So if I say that even number between 1 to 20, if I say set of all even numbers between 1 to 20. Even is a set of all numbers between 1 to 20. Between 1 to 20, including 1 and 20. It can be like a number can be greater than equal to 1 and less than equal to 20. If I say that even is a set of all the what elements it will contain? It will contain 2, 4, 6, 8, 10, 12, 14, 16, 18 and 20. There will no other elements inside this. So these are all even numbers from 1 to 20. Okay. So this we have how many numbers? 1, 2, 3. It is 4, 5, 6, 7, 8, 9, 10. So 10 elements are there in the. If I said how many elements denoted by small n, number of elements in even, it is 10. So when the number of elements is finite, we can count it. That is finite set. That is finite set. And if we cannot count the number of elements in a set, that is infinite set. Okay. So that is what here it is written, that for example the set of all prime numbers less than 20, when the limit is given, then it is finite set, while the set of all prime numbers is an infinite set. When there is no limit given and it is just said that set of all prime numbers, set of natural numbers, set of whole numbers, then that is infinite. Where we cannot count the number of elements in that set, that is infinite. And if we can count the number of elements in the set, that is finite. Okay. So we can say that what is the difference between them? Those sets whose elements we can count, those which are finite in number, that is finite set. Now see what is empty set. An empty set is a set that has no elements, means it is empty. It is also a set, but it is empty. It is denoted by phi. Generally, it is written like this, phi or this empty set. For example, the set of even prime numbers is an empty because there is no even number which is prime number. So that is set of all even prime number is empty set. Set of all even prime numbers are empty set. Okay. Now see singleton set. Singleton set is what? Singleton set is a set that contains only one element. Singleton set is a set that contains only one element. Like suppose I have a set name as A. See, generally the set name is denoted by capital letter. Okay. And inside this we have one element, 1, 2 or anything, one element is there only. Then that is called singleton set. Now see what is subset. A subset is a set that contains only elements that are also member of another set called superset. What does it mean? What does it mean? Okay, let me show you. Suppose we have one set A. Suppose we have one set A. A has 1, 2, 3, 4, 5. Okay. And if I say B contains 2 and 3. So this B has elements 2 and 3 which is inside A, which is A already has 2 and 3. So if B contain the elements which is present in the other set, this set is called the subset of A. This set is called the subset of A. Subset of A. And this is called the superset of B. This is called the superset of B. That is what here it is saying, that a subset is a set Subset is a set that contains only elements that are also member of another set called the superset. For example, 2, 4 is a subset of set of all even numbers. This can be another example of it. Okay, so let us move forward. And one thing I want to discuss about this subset, like what can be the subset of a set? We can have how many subset of a set? Here suppose A is this. When we are talking just now about this set A, so we can have how many subset of it? Or let us make a small set. Let us make a small set of this. So now we have this set A is containing 1, 2, 3. Okay. Suppose this set A contains 1, 2, 3. So the subset of A can be one empty set, or you can say phi set is subset of every set, is subset of every set phi. Okay, then we can have this one only, then we can have two only in a set, then we can have three only, this is another set. Then we can take two elements like 1 comma 2, then 1 comma 3, 2 comma 2 comma 3, then two elements we have taken 1 2 1 3 2 3. Set cannot repeat elements. Okay, so we cannot write 3 1 1 3 is already there, so we cannot write 3 1 or 3 2 2 3 is already there. So we are done with two elements. Now we can have three elements altogether. So this is a phi set, and this is the whole set, the set, same set A. So this all these are the subset of A. So how many subsets are there? 3. 1, 2, 3, 4, 5, 6, 7, 8. So if so how we can find the number of subsets of a set? We can have number of subset of a set is found using 2 to the power of number of elements. And suppose here n number of element is what? 3. So it is, for this example, it is 2 to the power of 3. So it is 8. That is, here we have seen just now that these are the 8 subset of this set A. These all are the subset of A. So any of them we can say this is also a subset of this, this is also a subset of this is also a subset of the same set is also called the subset of that set. Okay. So we have seen what is subset, and we have seen just now what is how many subsets we can have in a set. Now see what is universal set. What is universal set? So see, what a universal set is the set of all possible elements that can be used in a particular context. That can be used in a particular context. It can be set of all students in a particular class, set of all alphabets, set of any elements in a particular context. All the elements are considered in a universal set. See, for example, here the universal set of all even numbers can be the set of all integers. So that is universal set. Let us discuss in more detail. Like suppose if I take example that U is denoting universal set, and I am saying set of all elements from 1 to 100. Set of all elements from 1 to 100. So it will all 1, 2, 3 to till 100. It will be universal set. And then whatever the sets we will talk about here, all will element will be present in the universal set. Okay, so we can take elements from this universal set only. Like suppose we have 6, 80, 90. Suppose this one B 4, 9, 8, 50, 60, 70, 80, 90, and so on. So suppose till 90 we have this many elements are there in the B. So we can see that A is also containing the elements which is present in the universal set. B is also containing the elements from the universal set. So all these sets, whatever we will talk here now in this context, will be the subset of universal set. Will be the subset of universal set. Okay. So that is the meaning of universal set. It will contain all the elements, all the possible elements which we are talking in the particular context. And universal set is a set of all possible elements that can be used in a particular context. Okay. Now see, disjoint sets. For disjoint sets, two sets are disjoint if they have no common elements. If they have no common elements, for example, this set and this set. This set has one elements 1, 3 and 5, and this set has 2, 4 and 6. So they do not have any common element. They do not have any common element. Like you can see 1 is not present here, 3 is also not present here, 5 is also not present here. And same is here. 2 is not present here, 4 is not present here, 6 is not present in this set. So they both are disjoint. They both are disjoint. They do not have anything common. So they are disjoint. Now see the next, power set. So power set is a set of all possible subset of that set. Power set is the set of all possible subset of that set. It is called power set. Okay, it is called power set. So just now we have seen what are the subset of 1, 2, 3. We have seen one set here. We have seen set. Let me show you here. These are subset of A. This is the one subset, this is another subset, this is another subset, this is another subset. When we write this all subset inside a subset, inside a set, that is called power set. That is called power set. So if I make a curly brace, if I write this inside the curly brace, this, so this is called the power set of A. Power set of A. This is called power set of A. And if I just write like this, just like previously I had written, these are all subsets. These are all subsets. And if I ask you to write power set, just write this all the elements inside a set. Inside a set. For writing set, what we have to do, we have to write the all the elements inside the curly brace with comma. So we had already written the comma. You just put the curly brace before and at the end. So it now becomes the power set of A. So power set contains all the power set is the set of all subsets. Set of all subsets. So see, this one is the null set. This elements all containing one elements. This is containing two elements. This is containing two elements. This is two elements, and then the all three elements. So this is the power set of a set. Now see what is relations. So just now we have seen what are the what is the how many subsets we can have of a set. So we have found it is using formula 2 to the power of n. So the we can say that the cardinality or the number of elements in the power set will be 2 to the power of n. The number of elements of a set is known as cardinality of a set. The number of elements in a set is known as the cardinality of the set. Number of elements of a set is known as its cardinality of that set. Okay. So power set will contain 2 to the power of n number of elements. Okay, now we'll see what is relations. Now we'll see what is relations. See, relation is a connection between two or more objects. We can say that we have two sets. Suppose we have two sets A and B. So first we find the Cartesian product of A and B, and relation can be the subset of the Cartesian product of A and B if we want to find the relation from A cross B, from A to B. So let us understand here that suppose A is 1, 2, 3 and B is AB. So Cartesian product is written as A cross B. So what it will be? It is written as ordered pair. In the small parenthesis, the first element will be from the A and second element will be from B, and all the possible pairs will be made with each other. So one will be paired with A, one will be paired with B, now two will be paired with A, two will be paired with B, and three will be paired with A, three will be paired with B. So it is A cross B. Now relation can be the subset of this A cross B. Relation can be the subset of A cross B or the Cartesian product of two sets. If I say the relation from A to B, relation from A to B, so it is the subset of A cross B. Okay, can be the subset of A cross B. So that is here it is written relation is a connection. Relation is a connection between two or more objects. Between two or more objects. In mathematics, relation can be represented using ordered pairs where the first element is related to the second element. So for example, the relation less than can be represented by the ordered pair 2, 5. Okay, if I say relation less than, it can be represented by the ordered pair 2, 5, where 2 is less than 5, which means 2 is less than 5. So we can make a relation of such type of where the first one is less than the second one. So we'll see in detail about relations, different types of relations. Just now, first we discuss a little bit about functions because all these relations, sets, relations and functions are interrelated. Okay, so see, a function is a special type of relation where each input or domain, input is called domain. Each input value is uniquely associated with one output or range value. Okay. A function can be represented using a formula, a table or a graph. Okay. For example, the function fx is equal to x square. Function fx is equal to x square. What does it mean? The value we give it will be your input, and the result we are getting from this function when we put the value of x inside this, that will be your range or your output. So if suppose I say that x is 1, then fx is what? fx is 1 square is 1. So it is a 1 1. If I say the input is 2, so 2 square is 4. So and so on. We can find the values of the elements of this function. So let us move on to the relations. Let us see in detail about the different types of relations. Okay, so see what is this? Relations, we have just now seen that relations are used to describe the relationship between elements of set. Okay, so a relation is a set of ordered pairs. A relation is a set of ordered pairs where each ordered pair consists of two elements. And the first element is related to the second element. For example, if we have set A equal to 1, 2, 3 and set B equal to 4, 5, 6, and if we define a relation, we can define a relation R from A to B as R equal to 1, 4, 2, 5, 3, 6. This, what does it mean? It simply means 1 is related to 4, 2 is related to 5 and 3 is related to 6. Okay. We are writing this pair inside a relation R from A to B. It is from A to B. So first element, remember that first element will always be from set A and the second element will always be from set B in every ordered pair. And all those ordered pair which are written inside a relation, all these ordered pair elements, we say that the first element is related to the second element. Like here I have just now told that 1 is related to 4, 2 is related to 5 and 3 is related to 6 and so on. So relation plays important role in many areas of mathematics, computer science and engineering. For example, they can be used to model social networks, describe the behavior of computer programs, or analyze the performance of communication systems. Understanding the different types of relations and their properties is essential for developing effective mathematical models and algorithms. So now see, there are several types of relations in discrete mathematics. First one is reflexive relations. This is reflexive relation. Okay, first one. Okay, so let us now first name them. This is the second one, symmetric relation. Okay, this is symmetric relation. Then we have third one, transitive relation. Transitive relation. Then we have fourth one, anti-symmetric relation. Then we have equivalence relation. Equivalence relation. Okay, so these are the five main types of relations or the five important relations. First one is reflexive relation. So what is this reflexive relation? A relation R on a set A is reflexive if every element of A is related to itself. That is, for every A belongs to A and A belongs to R. Suppose we are say that R is a relation in which all the AA pairs are present, then for every elements of A, all AA pairs are present in a relation, then that is called reflexive relation. So let me write A. Suppose A is 1, 2, 3. Okay, 1, 2 and 3. So here when we say that if suppose I make A cross A cross A. So we have seen how to find the cross product of A cross B. So now I am talking just now that I am making the Cartesian product of A with itself. So suppose we have another set A named as A 1, 2, 3. Now when we make A cross A, it will be 1 1, 1 2, 1 3. Then 2 1, 2 2, 2 3. Then 3 1, 3 2, 3 3. So basically, if you see these elements in which the first and the second element both are same, in which first and second element both are same, these are called the reflexive pair. And if I make a relation R from this A cross A, R from A cross A, which contain these elements, in which both first and the second element are same, 1 1, 2 2, 3 3. All these pairs are present in a relation, then that relation is called reflexive relation. That relation is called reflexive relation. These are called the reflexive pairs. And any other elements, if it is present is that, suppose I have another relation R1 in which other elements are also present, that is also okay. It is just saying that all these reflexive pairs should be present in a relation, then that relation is called reflexive relation. Suppose we have this one more element, one more ordered pair present in this. This is called the also called the reflexive relation. See here what it is saying, that reflexive relation R on a set A is reflexive if every element of A is related to itself. If every element of A is related to itself. Okay. It is saying that, in other words, for every A belongs to capital A, small a belongs to R. A belongs to R means for every element of A. Small a is varying for every element of A. It can be B, it can be C. So all these reflexive pairs, the diagonal elements we have just now seen, like 1 1, 2 2, 3 3. These are AA pairs called. It is called AA pairs or reflexive pairs. It is present in this relation. If it is all these reflexive pairs are present in a relation, then that relation is called reflexive relation. Okay. Now see, this is what is symmetric relation. A relation R on a set A is symmetric if every A comma B belongs to R, then B comma A should belong to R. If for every A comma B means every element present in the relation, if it is AB, then BA should be present in the R. That is the meaning of this. That is the meaning of it. Like suppose if I say that 3 4 is present in a relation, then 4 3 should also be present in the relation. If it is present like this, all the elements which are present in this form AB, all its BA pair should be present in that, then that is called symmetric relation. Suppose the reflexive pair is present, 1 1. So this also we can say AB. So in this case, when we find the BA of it is same. BA of it is also same. So it is present. So for reflexive pairs, we do not need to check if it is reflexive. Then reflexive pairs, for the reflexive pairs, symmetric pairs are present. So we do not need to care about the reflexive pair. But for other elements, we have to check whether its symmetric pair is present or not. If symmetric pair is not present, then we can say that this is not a symmetric relation. This is not a symmetric relation. Okay, so we can say that this is not a symmetric relation. Suppose I have this relation R1, R2. Suppose I have this one 1 1, 2 2 and 2 3. 2 3 and 3 comma 2. If it is there in a relation R2, so 1 1, it is reflexive pair, so we do not need to check. Suppose we are checking for symmetric or not. Symmetric or not. So how we'll check? For reflexive pair, we do not need to check because AB, BA is present. Because the BA of this is also the same. Here 2 2, it is also reflexive pair, but this one is not a reflexive pair, it is AB pair. We have to put in the order BA. So 3 2, we have to check whether 3 2 is present or not in this relation. So we see that 3 2 is also present in this. For 3 2, 2 3 is this one. So both are present in this relation. So this is symmetric relation. This is symmetric relation. But if I ask you whether it is reflexive relation or not, so the since we have made this relation from the relation A, from the set A using A cross A, we have found this relation R. So R2, all the reflexive pairs are not present. Here 3 3 is not present. 3 3 is not present, so it is not a reflexive relation. It is not a reflexive relation. That is why it is not a reflexive relation. Okay. But it is a symmetric relation. It is because all those pairs which are present in this relation, its symmetric pair is present in this relation. So the condition for the symmetric relation is for all the AB pairs present in this relation, BA pair should be present in this relation. So here we are seeing that for 2 3 3 2 is present. So it is a symmetric relation. Okay. Now let us see about the other type of relations. So third one is transitive relation. So what is this transitive relation? So see, the transitive relation, a relation R on a set A is transitive if for every AB belongs to R and BC belongs to R. Means AB belongs to R and BC belongs to R, then AC should belongs to R. If such type of condition follows, then we can say that the relation is transitive relation. For every A, B belongs to R and B, C belongs to R, then AC should belongs to R. What does it mean? See carefully. A, B, and here it is B, C. So here B is common in both. Its second element is B and its first element is B. So that is, you need to take care of that. The second element of this one is B and the first element of this one is B. So if such type of relations are there, such type of relation ordered pairs are present, then A comma C should be present. A comma C should be present in that relation. Then only that relation is called transitive relation. Like suppose I have a relation R3. Like suppose I have 1 2 and I have 2 3 present in a relation, then 1 3 should be also be present in the relation, then that is called transitive relation. That is called transitive relation. Okay, that is called transitive relation. If it is not present for every pair, subcheck for every pair 1 2 2 3, 1 3 should be present. Like suppose we have another relation R4. This is transitive. This is transitive. Now we see that we have another relation 1 2 2 3, and suppose we have 1 3 is present. Okay, but suppose we have 3 1. 3 1 is present here in this relation. So for 1 2 and 2 3, since this is 2 2 is common, so we need to have 1 3 pair also. So for this we see that 1 3 is present. For this we see that 1 3 is present. 1 3 is present. So we can see, till now we can see that it is following the property of transitivity. But for this 1 3 and 3 1, here also 3 3 is same. So this 1 1 should be present in this relation to make it transitive. For every pair of elements present in this, AB and BC is present, then for that AC should be there. AC should be there. So for this AC will be what? 1 1. So it should also be present in this relation. But since it is not present, so we can say that this is relation is not transitive. We have to see every pair of elements, every ordered pairs we have to check. Okay, then only we can say that it is that type of relation or not. Okay, so we have to check the condition for every element set relations. Like just now we were talking about transitive relation, so we have to see that for every AB belongs to R and BC belongs to R, AC should belong to R. Then only we can say that that relation is a transitive relation.